So now our next objective is frequency translation for practical antenna size. Okay. Fine. So based on our experience, we already know if we choose a simple LTI network, okay, let's say we have a 2-port linear and time invariant LTI network, then if we feed a signal X at some frequency F in and we observe the signal Y, let's say its frequency F out, it turns out that if it is going to be an LTI system, then F out has to be equal to F in. So the steady state frequency of the output signal has to be equal to the steady state frequency of the input signal. This we have already studied from this we already know from the signal systems course. So it means that such a system or such a network is not useful for frequency translation. Okay. So LTI network cannot perform frequency translation. Okay, so what else can be done? Definitely LTI systems are not sufficient to do this job. So we have to change at least one of these constraint. Okay, so either we have to see if a nonlinear time invariant network can perform this job or a linear time variant system can do this job. Okay, so this is what we are going to try out. So first we will see whether a nonlinear time invariant network can help in the frequency translation. So let's nonlinear time invariant. This is X, Y. So when we say nonlinear, so this Y and X will be related by a nonlinear, for example, nonlinear polynomial. And here we are already assuming that there is no memory in the system. So even if there is a memory, the discussion, whatever we are going to do, will be still relevant. Okay. So we are just taking a simple case where there is no memory. So this Y is some function, nonlinear function of X, like Y is some constant plus some linear term, then quadratic nonlinearity, then cubic, and so on. Okay. So we want to see if such a system can perform frequency translation. And to do that, we'll take an example where X is a simple sinusoidal signal. So let's say having an amplitude of A at an angular frequency of omega. So in such a scenario, we can see that this y is going to be in this form. Naught plus a1 a sine omega t plus a2 a square sine square omega t plus a3 a cube sine cube omega t and so on. From here, see that the output has so many terms. But first term is going to be just a constant, won't change with time. Second term is a scaled function of input itself. Okay, so there is no change in the frequency. But if we look at the nonlinear terms, okay, so for example, starting with this quadratic term, here we can rewrite this sine square omega t as 1 minus cos 2 omega t divided by 2. And similarly, we can write a cube sine cube omega t as a cube. Cubic term can be written as a3 a cube, and using the trigonometric identity for sine cube theta, we can write sine cube omega t as 3 sine omega t minus sine 3 omega t divided by 4. Okay. And so on. If we have more terms, accordingly, we will be able to convert those terms into, if using trigonometric identity, into a form where we can talk about the frequency content of contribution from those specific terms. Okay. So here, if we rearrange, right now, let's talk about only the nonlinearity till the third order. Okay. See that this guy, first term is only contributing constant, which is a DC term. Okay. Second term, because of the linear component, is giving rise to signal at frequency omega, which is same as the input frequency. Whereas the quadratic term is giving a DC term as well as a term which is at a second harmonic. Okay, this is at a frequency 2 omega. So here we get DC as well as 2 omega. And looking at the cubic nonlinearity, we can see it is contributing to a term at the fundamental frequency omega, the input frequency, and at the third harmonic. So very easily we can see that as the number of the order of the nonlinearity is going to increase, the number of harmonics which you are going to get is also going to increase. So the basic idea is, with the help of this nonlinear term, or with the help of such a nonlinear network, we can take an input frequency at omega and we can generate frequencies which are different from omega. So in a way, this does the frequency translation which we wanted. But the issue is, it is generating a lot of nonlinear terms. And if we really want to change the frequency by a large amount, this may not be a practical solution. So the conclusion is, nonlinearity gives rise to frequency translation. It generates large number of undesired harmonic components. Sometimes it may be not so bad. There are some applications where you may want to actually generate a large number of harmonics, but many cases this may not do the job. But for some applications where the frequency needs to be only doubled or tripled, uh, for such system, this approach may still work out. Hmm? So in our application, if we look at, so our frequency is very low, okay, 1 kilohertz, which is giving rise to a wavelength, guided wavelength of hundreds of kilometers. So this we want to reduce to the factor, to the order of, let's say, meter or centimeters. So you can easily see that to do this huge reduction in the guided wavelength, this output frequency of this network has to be increased by several orders of magnitude. And obviously, by using this simple non-linearity, is not going to result in a desired output frequency, because we may need the non-linear terms which are of the order of say 100 to 200 and so on, okay, which is very impractical. Next approach we will do is by utilizing time variance. So we'll be talking about a network which is linear but time variant. Here also we will apply signal at a frequency f in, and we will try to observe what kind of frequencies may be present in the output. So as to find whether this network is going to perform the required frequency translation, first thing what we are going to do is we will try to understand what is a time variant network, and at least we will take a simple example to understand the requirement, means understand the functionality of a time variant network. And using that example, we will try to demonstrate if frequency translation is feasible or not. So when we say we want a time variant network, the simplest network which we can think of is simple gain block, okay, where you apply a signal time domain, and ideally this is y is going to be just a times x of t. But if it is a time variant network, then this gain itself is a function of time. So the output is going to be a of t times x of t. Okay, so this is a good example of a time variant but linear network. So it's becoming time variant because of the gain being function of time. Now let's take an example where a of t is a periodic function of time. So let me say it is something like a naught cos omega naught t. Okay. And we will go back to our same example where x of t is also a sinusoid at frequency, say, omega n. So the y of t is going to be a of t multiplied by x of t, which is a naught cos omega naught t multiplied a sine omega n t. And if we use a simple trigonometry, we can easily see that this is same as a naught a sine omega naught t plus omega n t plus sine omega n t minus omega naught t divided by 2, which can be rewritten as a naught a by 2 sine of omega naught plus omega n into t plus sine of omega n minus omega naught t. And now we can easily observe that if we look at the frequency content in the output signal, it has from first term it is containing a signal at frequency omega naught plus omega n, and from the second term it is containing signal at frequency omega n minus omega naught. Let us look at the spectrum of the signal to get a better idea about how is this frequency translation helping in this scenario. So if I draw the magnitudes of x and y, the input and the output signal in the frequency domain, let's say our input signal, which is a single tone, is sitting at this frequency fn. In our audio system example, this frequency was around 1 kilohertz, correct? Really small. And let's say the frequency of this time varying gain, which is this omega naught, okay, and correspondingly the so for this angular frequency there is the frequency f naught associated. So let me assume that that is here at frequency f naught. Then what we have seen by doing this simple analytical calculation is that we will be getting two signals at frequencies omega naught plus omega in and omega minus omega naught. So we are looking at the single-sided spectrum, and the way I am showing f naught is much higher than f in. Then the two frequencies are going to appear at f naught plus this is going to be at f naught plus f in, and another one is omega in or f in minus f naught, which is same as f naught minus f in. Okay, because for the real signals there will be the equal strength and at the negative frequency as well as at the positive frequency. So I need not show the negative frequency here. I will show only the positive frequency, which is f naught minus f in. And if the strength here is A and this gauge strength is A naught, we have seen that the strength of these two signals are going to be A times A naught by 2. And it is very obvious that we started with some frequency F in, and it has given rise to signal and frequency much higher than F in. So compared to the previous approach of nonlinear network, this approach looks much more promising, as it gives you an ability to increase the input frequency by much higher value with a very simple periodic time varying operation. So if I summarize this approach looks like we have taken the low frequency electrical signal and we pass it through a gain which is time varying. So this time varying gain I can show as some kind of multiplication with a time varying signal. Okay, here I can say, so this is a multiplier block. I am multiplying this input signal with a periodic time varying signal, and this block inside this box is acting like a periodically time varying gain. And once I get this output, what I can do, I can feed it to an antenna, and now this antenna will be able to even with a much smaller physical size, it can be able to radiate very efficiently. Okay, so earlier we had this strong trade-off between the input signal frequency and the physical size of the antenna. Right now we can see that trade-off is no longer there because we can independently choose this omega naught frequency, which needs to be multiplied with the input frequency. Conclusion is antenna size is reduced by taking advantage of frequency translation by linear time varying. Okay. So just to keep in mind the way we are doing, this is not just a time varying network, it is also periodically time varying because this function is periodic with time. So we can call it an LP TV network. Okay. PTV means linear periodically time varying. Okay. So from now onwards, what we will do, we will use this approach for frequency translation, and we will try to see which all practical problems we are going to face. So here we have looked at a simple transmitter design where the signal at a very low small frequency can be converted to a higher frequency and then radiated efficiently by a compact antenna. Okay, so this is at F low, and here we have a high frequency. Next, we will try to see how to design a receiver, and do we face the same kind of problem as we have seen in the design of a transmitter. This is simple transmitter. Okay.